Okay, we've gotten two answers. So if you haven't done it, then just try to finish it, but I'll go over it. So we can turn this equation into a quadratic. And the way we do this is by multiplying by x, as Eric has annotated. So we get x squared equals x plus 1. This gives us x squared minus x minus 1 equals 0. We can use the quadratic formula. And actually, I'll just write the quadratic formula if you forgot it. It's negative b plus or minus square root b squared minus 4ac all over 2a. And this is equal, for our equation, is equal to 1 plus or minus square root 1 minus 4 times 1 times negative 1 over 2. This is equal to 1 plus or minus square root 5 over 2. So everyone who got it, good job. And let's move on to the next problem.
So I know this is a cubic function, but Vietas, as I mentioned earlier, can be applied to any sort of polynomial. Okay, so Albert, can you let annotating? So we have a cubic polynomial has 3 positive integer roots, and by Vietas we know that if the roots are x, y, and z, you know x times y times z is 2010, and we know that x plus y plus z equals a. And notice that it's not negative 2010, because if you have the polynomial or factorization x, I shouldn't have x, y, z actually. I should have like a, b, and c. Yeah, let's do a plus b, a, b, c, and a plus b plus c. I'll just do this is p and this is not a, this is p. You get the point. I just don't want to use the same variables. So it's 2010 because if our factorization should be x minus a times x minus b times x minus c. And notice that our constant term that has no x is negative a times negative b times negative c, and that's negative abc. So that means negative abc is 2010, and you take away the negatives, and you get abc, where the product is 2010. It also says there are 3 positive integers. So that means that we just need to factorize 2010. And 2010 can be factorized as 2 actually, times 3 times 5 times 67, I think. Yeah. Maybe factorized as 2 times 3 times 5 is 67. And if we want to minimize a, we want, or p, we want a, the roots, the sum to be minimal. And that only occurs when we multiply the first 2 roots to a 6, 5, and 67. Because we have 4 numbers here, well, there's only 3 roots. Because the fundamental theorem of algebra states that a polynomial of highest degree x will have x solutions. So we have 3 solutions, but we have 10 factors. So 2 need to be combined. So it's 6, 5, and 67. Notice that if we combine, let's say 3 and 5, that would give us a bigger a, because it would be 2 plus 15 plus 67. And this is only what 78. So our answer is A.
Okay, so that was problem 3. Let's move on to problem 4. And it's this one right here. The quadratic equation x squared plus mx plus n has roots twice of x squared plus px plus m, and none of m, n, and p is 0. What is the value of n over p? Now, twice those means each of the roots is 2 times the other roots of the other quadratic. So that's twice those, and yeah. Okay, I'm just gonna go over it. I didn't get much answers, but that's all right. Is not the easiest problem. So, all right. So the quadratic equation x squared plus mx plus n has roots twice those x squared plus px plus m, and none of m, n, and p is 0. So what is the value of n over p? So let's call the two roots a and b. Okay, that means that m, according to Vieta's formulas, is equal to negative a minus b. And this is because this is equal to negative, the sum of the roots is equal to negative m. So negative m equals a plus b, and therefore m equals negative a minus b. So that's how we get m equals negative a minus b. Next, let's go to n, and n is just equal to ab. Okay, now let's go to p. Now, using the same method, we can get p is equal to, oh wait, oh, this is negative 2a minus 2b. I forgot that m was the one being 2 times that. That's my bad. That means n is not actually ab. So if we have these two roots a and b, that means that this equation right here is x minus 2a times x minus 2b, because it's 2 times the roots. So n is actually 4ab. P is negative a minus b, and m, well, we already know m is equal to negative 2a minus 2b, right? But it's also equal to ab. So now we know that n over p is equal to 4ab over negative a minus b, which is equal to 4m over m over 2, because as we notice, m, 1/2 m is negative a minus b, and four times m, or 4 and is equal to 8. So our answer is D, which is 8. So using Vieta's, we can get some pretty satisfying equations that cancel out. That's how we get n over p. All right. So that's question 4. Let's move on to the next question.
So I'll explain. This is a pretty hard problem. I think this is 2017 problem 23. So the problem says for certain real numbers a, b, and c, the polynomial g of x equals x cubed plus ax squared plus x plus 10 has 3 distinct roots, and each root of g of x is also a root of the polynomial f of x, which is x to the 4 plus x cubed plus bx squared plus 100x plus c, and you're asked to find f of 1. So I'll write g of x. It says it is x cubed plus ax squared plus x plus 10. And f of x is x4 plus x cubed plus bx squared plus 100x plus c. So if we let the roots of g of x be p, q, and r, we know that because of Vietas, we know that p plus q plus r equals negative a, and p, q, r equals PQR equals negative 10. And since we know the roots are PQR, and we know that f of x has the same roots, but one more, the roots of this we can call PQRS. And we know that P plus Q plus R plus S is -1. And you use these two to get that S equals A minus 1. And now, since we know this, the PQR equals -10. And we also know that through Vietas formulas, on the linear term of g of x, we know that PQ plus QR plus PR equals 1. And we also know that from the linear term of f of x, PQR plus PQS plus PRS plus QRS is 100. Is 100, and actually, sorry, -100. So that's actually -100. And so you substitute, you substitute PQR to get that -10 plus S equals -100. So we know that S equals -90. So this is our fourth root. And also it follows that since we know this, A equals -89, and we can factor f of x in terms of g of x because they share the same roots other than this s. So we know f of x equals x minus 90 g of x. And actually this, yeah, plus 90. So that means that f of 1 equals 91 times g of 1. And since we know a, you can just plug in 1 and multiply it by 99. So this, when you plug in 1 here, it's 77, and 77 times 91 just happens to be -7,700, -7,007. It's a bit complicated, but it really uses Vieta's formulas in a really good way. So if you want to do it later, you can definitely try. But that is that problem. Yeah. So now our next problem is, how many ordered pairs of positive integers b and c exist where both x squared plus bx plus c equals 0 and x squared plus cx plus b do not have distinct real solutions? I think I found this from last year's AMC 10. So this is pretty recent, and yeah. Oh, me and Albert both got this wrong actually on the real AMC 10. So it's a bit confusing, but I think you guys can get it.
Okay, so I'm going to go over the problem now. How many ordered pairs of positive integers b and c exist where both x squared plus bx plus c equals 0 and x squared plus cx plus b equals 0 do not have distinct real solutions? So when a quadratic does not have distinct real solutions, it means that the discriminant is either zero or negative. When it's zero, it has only one solution, and when it's negative, it has no real solutions. So we need to make sure that the discriminant is greater than or equal to 0. So the discriminant is for this equation right here, b squared minus 4ac, and the discriminant for this one is the square root of c squared minus 4 ab. And in this case, a is just 1, so basically the discriminant is gonna ignore this a, and we need to make sure we can set up two inequalities here. B squared minus 4c is less than or equal to 0, and c squared minus 4b is less than or equal to 0. Now we can just do casework here, but we can actually simplify further. If we move this to the other side, we get c squared is less than or equal to 4b, and this, and if we square this, which would be helpful later, we'll get c to the 4th is less than or equal to 16b squared. Now we multiply this equation by 16 to get 16b squared minus 64c is less than or equal to 0. Now we can set up another inequality. If first we make this into 64c, and now that means that c to the 4th is less than or equal to 16b squared, which is less than 64c. And now we can do casework using this equation. All right. So c to the 4th is less than 16b squared is less than or equal to 64c. All right, let's just try out numbers. So since they both have to be positive integers, it could be 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, and 4, 4. And these are all of the solutions, because as b gets bigger, c will have to get right here 64c will have to get even larger, but that means c to the 4th won't be less than 16b squared. So these are all the solutions. And there's yeah, exponentially this grows faster than this. We don't really have any more solutions, and therefore the answer is B, 6. So that's how you do this problem. Let's move on to the next one. The real numbers C, B, A form an arithmetic sequence with A is greater than or equal to B, is greater than or equal to C, is greater than or equal to 0. The quadratic AX squared plus BX plus C has exactly one root. What is this root?
So I'll explain the problem, I guess. So, if we write A, well, we can write B as the average of A and C. Because it's an arithmetic sequence. And because it has one real root, the discriminant is 0. So we need to find the unique root, negative b over 2a. That's what we're trying to find. And because we know the discriminant is b squared minus 4ac is 0, we know that b squared equals 4ac. And you get that if you divide by, or if you use substitution, I guess, into this negative b over 2a, you get that negative b over 2a equals negative 2c over b. And this gives you, this basically is this, but in a different form. Then, let's see, what did I do? Okay, so we substitute b. I substituted b as a plus c over 2 and into here. And that gives me like, I get 1 over a plus 4c over 4 equals 2c over b. You just bunch of substitution, and what you're trying to find is a over c, and you plug in again, I guess, and you get a quadratic in a over c. A over c squared minus 14 a over c plus 1 equals 0. So this is our quadratic, and I'll clear and rewrite it. So if a over c is my x, I have x squared minus 14x plus 14x plus 1 equals 0. That's it. I'm gonna use the formula, and this gives you a over c equals 7 plus minus 4 root 3. But notice that the constraint a is greater than b, or it's in descending order, it's a, b, c. Note that 7 minus 4 root 3 is less than 1. So this violates the fact, or less than 0, that violates this inequality. So it has to be 7 plus 4 root 3. And then you plug in what we had, the negative b over 2a. We simplified that, and that was 1 over a plus 4c over 4. Is that right? Wait, there should not be a, where is this? It should be, oh, I don't think it's working. Oh, it's not that, but it's 1 over a over 2c 4c plus 1 over 4. And then you plug it in, and what you get is 2 minus 3. So yeah, it's 6:30. So thank you guys for coming. And I guess
Yeah.
we can end it now.
Yeah, thank you for the lesson. It was very informational. I learned a lot. Thank you.
Thank you.
Yeah.